Next, we have our eminent speaker, Dr. Abdul Nasser here. So he's
Adel
from
Nasser, yes.
Yeah.
Adel
So he's from Adel Nasser. Okay, Adel Nasser.
Okay.
Sorry.
No, it's
Adel
all right.
Nasser.
I mean, I get
So
called
he's
the old name in this country, but you know, that's all right.
okay. So he's from Department of Mechanical, Aerospace, Civil Engineering, Faculty of Science and Engineering, University of Manchester, UK. So he is ready to share his experience and impact of using an PCM metal foam composites on latent heat thermal energy storage process. So just a small gist about him: mechanical engineering graduate from Faculty of Engineering, University of El Fatih, Libya, followed by MSc in computational methods and fluid mechanics from Aeronautical and Mechanical Engineering Department, University of Salford. Then he joined the Thermo and Fluid Divisions of Mechanical Engineering Department at UMIST as a researcher. Then he went back to Salford University for 5 years to work on number of projects. So he has done so many research projects, which has been flourished for more than 19 years, I think so. So University of Manchester is having a privilege to have him in this position. Then with a small intro, I would like to invite our speaker to share his experience to the audience. Thank you, sir. The session is yours.
Thank you, Dr. Adam. You are a very kind man, and I appreciate your introduction. Thank you. I'm very humbled to hear it. Thank you.
Thank you, sir. It's all our blessings. Thank you, sir.
Okay, thank you. Right, everybody. Thank you for coming to this session. Really, the real work we are representing today, all the credit for it to go to Dr. Ahmed or Dr. Sharwan or Dr. Nabil, because those are the one, they really deliver the result. We just talk together and they go and do the hard work. They come back with the result. So every credit in this representation goes back to them. What we're gonna talk today is about the subject of the use of green energy and moving from fossil fuel to green energy and the problem that we have with the use of the green energy. Recently, BCM, which phase changing material, became one of the topics that many people use to enhance the effectiveness of the green energy. So today, the reason for this is actually this picture, which is a very old picture, but it's detecting how much carbon dioxide will be generated for different increase in temperature around us. And this is what we're talking about, the green gas and the impact on our life and our world. And many of us can see these days in floods and rains, all these things. So these are, from here is the current situation, and these are the various prediction that how bad is gonna go in the amount of carbon dioxide that will be produced if we don't do something about it. The other part of this, everybody knows that the national world have, or the world came together and decide all carbon dioxide should not go be above the 2 degrees centigrade to save our world. So this is the range when we are targeting. And we're gonna do this by reducing our carbon dioxide. And this is why we are from fossil fuel energy to renewable energy. One of the good things about the renewable energy is available and is free and environment friendly as well. Most of the people these days, they use wind energy like Sharwan have done in his representation, and solar energy is another popular renewable energy. But the problem with them, the temperature during the day is varying, and during the night there is no sun at all, so there is no energy that we can use. So it is intermittent as well as variable. So, but the need of electricity is not even goes up and down, it is always increasing. So the discrepancies between the amount of energy supplied and the energy demand is imbalanced. And this is where many people sees storing the spare energy when we have a lot of it is a good way forward, so we can use it when we can. So the energy store technology, this assemble picture which we are focusing on. Obviously there is other ways, but energy store at the moment, it can be mechanical, electrochemical, chemical, or thermo energy. We will be focusing in thermo energy. Why? Electrothermal is basically, we are talking about batteries, okay? Mechanical, this is when we are talking about the flywheel and the hydro energy, the pumped hydro energy. When chemical engineering, we're gonna talk about a lot of chemical component that can be break down into a small component by using the heat and save them separately, then bring them together when we need the energy. This is where most of our work in our group in this area, we did some work on hydrogen, but this is the one we normally consume, especially the latent heat. This technique which is sensible heat store, latent heat, or thermochemical one. These are advantage and disadvantage of each technique. To appreciate these properties, I think we need to look at, no, I don't think I included here. The difference between sorry guys. The difference between sensible energy and heat energy, the sensible energy, it uses things like water, molten salt, where you only heat it up. So it doesn't change its status, but it keeps absorbing energy up to a certain limit. If we want more energy to store, that means we need a bigger quantity of this material, and hence we will be looking at a bigger volume or a bigger container. The advantage of the latent heat energy store, we use a material that it changes from solid to liquid or from liquid to solid by energy at a sensible temperature. So it absorbs too much energy to move from one status to another. Okay, the thermochemical store is basically a chemical reaction. So what we're going to be focusing on is latent heat energy. How do people use changing material in our model, we said we're gonna use phase changing material with a metal form. Metal form is basically like a sponge, but it's made from metal. And we'll cover this metal form paraffin, which is changing, phase changing material. And this is something Dr. Ahmed have
Rakim,
out of the literature survey. Yes.
Rakim Al-Sabar. Rakim, please mute your mic. It is disturbing others. Rakim. Yes, Professor, please proceed. Sorry.
Thank you, Dr. Adel. So here, if we have this sponge metal one, we warm or heat this BCM material becomes like liquid down the frame, the structure in it, or the sponge in it, the metal sponge or the metal foam in it, and leave it there to cool. When you bring it up, the paraffin itself is cover all the structure of the foam. And this is where now this combination between BCM and metal foam is a kind of media, storing media that we're going to use to enhance our thermal energy. So the foams, this is how it look like. Okay, there is two examples here. Okay, there is the nickel one with a different, here we have 5 holes or pores per inch. Here we have 10, here we have 25. So even that, there is a various type of structure that we can use, and each one of them will have a different capacity for the heat. So if we use this with the paraffin, this is a kind of BCM material we'll be able to use in practice. I have another example, which we have a copper, and again, different sizes, and we cover it with paraffin. Now we're gonna use one of those to explain the advantage of what we just did. The advantage of mixing BCM material and metal foam. And think that was one of the very early paper that Dr. Ahmed have produced. What was our test study or the case study that we have? We have a tank or rectangular. Inside it, there is, we filled it up with the BCM metal foam we just created. We cover this around it by a layer of the metal foam. It's a different one, or, you know, that doesn't matter. Then we have a channel where the air goes from this side, go around here, and come out from the other side. So this is basically the problem that we were trying to solve. These are the property which it comes with the paraffin, okay? And in order to enhance the rate of change of our system, cover foam is used to improve the thermal conductivity, as I just said. What's happening to the questions? Don't show me up. Okay. I think the animation is not working in this, but it doesn't matter. I am going to explain. Anybody of engineer, he will know what governing equation is. As Dr. Sharwan just said, we have continuity equation and have momentum equation. In this equation here, we have few new terms appeared which represent the inclusion of phase changing material. There is phi here represent what we call it porosity, and C and at the K, which is called inertia resistance. Those terms here is the viscous term, as you can see mu here, and this here, we call it inertia term. But those terms I just pointed out, those three terms are not readily available, and we need to use some empirical formula to be able to calculate them. I will show you some of them. So this is continuity equation, momentum equation. Then we're gonna move to energy equation. We have fluid and we have solid. There is between them interaction. So when the fluid is hot, it hot the material, and this here through those what we call it exchange term, okay? Exchange heat term. All right, those terms here represent the, what they call it, interfacial energy coefficient, okay? And you can see here one for the solid SHF and SHF. Those are again very important parameters, which they call it effective term for conductivity for liquid and solid. This is obviously the conducting surface energy equation. So those, for us to solve those two systems, we need some empirical formulas. So I'm not gonna give you any headache by going through them, but this is the permeability, the inertial coefficient. And again, if we go here, we have interfacial specific area. All those values we have actually included in the calculation. One new term to you is what we call it liquid friction or the solid friction, which is the amount of liquid in the combination. We'll understand, we'll talk about that in a few minutes. So let me see now if it's gonna work without a problem. Yes, so for the problem we just described or show you earlier on, we have this boundary condition. The mass flow in for the water is equal, the one is coming out, and there is a temperature for the, at the outlet, we're using the gradient, the zero gradient condition. And this is sort of, at the wall, we have various terms which represent the heat and temperature going through the system. Right. Operating condition here, we will be giving our result at volumetric flow of 0.5 meter cube per hour, and the water temperature is going in is at 80 degree and paraffin initial temperature 16. We're going to have, you remember when we talked about the copper form characteristic, you have the cell, and this cell of BCM is covered or surrounded by metal form. These are the basic value that we use when we calculated our simulation initially. All right, then we done some specific calculation, okay, to have the effect of changing variability and changing the pore size, which is how many pores per inch. Then we studied after this is the thickness of the layer we put of the paraffin on the structure as well. So this is where you relax, and I'm gonna just keep ticking. This is the one which is pure paraffin. This is the one with copper and paraffin. The fluid is going from this side and going out. We need to see our aim is to see how quickly the system is absorbing heat, or because when it absorbs heat, this means I'm storing heat, right? And when I store heat, I'm basically letting the heat will move the BCM from a solid state to a liquid state. So let's see how quickly this happens. So this is the pure, this is the BCM, the composite or the composition that we made. So after 10 minutes, 15 minutes, 20 minutes, you see, this is how quickly our paraffin composite is absorbing heat and moving from being solid to being liquid. And here is really much slower process. This is where I should have told you one of the characteristics of any store system is how quickly they do their charging process and their discharging process. When I say charging process, I'm giving them a heating, storing, so this heat will melt whatever storing material I'm using. So now the heat I'm pushing it in, and now they are using the paraffin, and the cupboard is absorbing more heating, and they keep moving forward, right? So now we reach a stage when actually there is sufficient heat, that's it, is 100% is being melted, while here it's keep still going on. I think it's gonna go up to 90 minutes. These are the difference between paraffin in its own. It took 90 minutes to store energy, while when I'm using a composite storing material, which a combination between the copper and the paraffin, I'm doing it faster. This graph will explain what I'm saying in a more logic way. Okay, theta here is a normalized temperature. So whatever the temperature to go from 1 to 0, alpha is the solid fraction that we talked about it, how many solid in the mixture. Here we're saying there is 0 solid in the mixture, here we're saying 1. So the dotted 1, okay, for the for the solid fraction, and the solid line for the pure paraffin. So if we look here, this is as the temperature goes, the solid reduce in their value or amount of solid in there until you come to a point when after this, your solid melt a little bit. It becomes mushy. So it's now moving from a mushy state, more mushy, and more fluent until becomes to certain time when every bit of solid is being converted to liquid. It's the same here. You notice here for the pure paraffin, it needed 40 minutes to start melting, while for the composite one is only 20, so it's nearly half the time. After this, so this is initially just to give you impression of how quickly, sorry guys, I'm gonna speed up, okay, it's already 1:30, sorry. Then we did some calculation for the various porosity values, okay? And you can see the bigger the porosity value, the more time is needed to melt. So our alpha here is here at 0.8, but alpha at 0.9 is higher there. So the amount of solid that is being converted to liquid at the value of 0.8 is higher, is less than the one at 0.8. We did this experiment for various bore size, okay, 5, 10. So now I'm gonna speed up. Now what we did as well, we did calculation to study the thickness on the top of the metal, how much paraffin thickness we use. Again, you can see that it goes from 0 to 1. So again, with time, the slope here is smaller, so it takes less time with a smaller system than larger system. And this is where I give my conclusion. So definitely using a composite PCM with metal form will improve the charging rate, and this is charging rate as well, obviously nearly by 50% of the time. So adding metal form layer on the structure, making it thicker, the metal form itself, that again increase the charging process, and this is charging process. Reducing the porosity, as we saw from the picture, improve the charging rate achieved. And the bore size, which is the one, how many hole per inch, again has transparent to be, has no significance on the rate of change. Okay, and this is where I finish. And yes, this is the list of the papers that Dr. Ahmed have been working on. So thank you, Dr. Ahmed. And this is when I say thank you, and obviously thank Dr. Nouby for inviting us, and we hope that will be start for more collaboration. Thank you.
The thanks is for you, Adel.
Any questions?